Hi, my name's Emily and I'm going to be explaining problem number 3 in the 2011 Calculus AB FRQ. The problem gives you a region R enclosed by two graphs, f of x and g of x. Part A asks you to write an equation for the line tangent to the graph of f at x equals 1/2. So first, we should identify which curve in the figure is f of x and g of x, as it is not given to us explicitly. So we should know the graph of sine, which looks like this. Therefore, this line here should be our g of x, which is a sine function. Then this other curve is f of x. Now that we have identified those, which we will be using in part B, we can move on to the problem. This may seem hard, but you can do it. To find the equation of the tangent line on x equals 1/2 for function f, we need to first find the slope to plug into our point slope equation, y minus y sub 1 equals m times x minus x sub 1. We know that the slope will be the first derivative of f of x, which is f prime of x. Using the power rule, we can determine that the slope will be 24x squared. Since we are finding the slope at x equals 1/2, we will plug that into the equation of f prime of x. This gives us 6, which is our slope, or the m value. The given point in the graph at x equals 1/2 is 1/2, 1. We can plug this in to our x sub 1 and y sub 1 values. This gives us the equation y minus 1 equals 6 times x minus 1/2, which simplifies to y equals 6 minus 1/2 plus 1 if we isolate the y. This is the equation to the line tangent to the curve of f at x equals 1/2 and is our final answer to section A. Part B asks for the area of R. The area between two curves can be found using one of two formulas, one which is in terms of x and the other which is in terms of y. However, since the problem gives us two functions, f of x and g of x, which are both in terms of x, we are going to use this upper integral. We need to find a and b, which will be the x value interval that the area lies between. We also need to determine which curve lies above the area and which curve lies below the area to plug in as our f of x and g of x in the integral expression. Note that the f of x and g of x in the integral expression is not the same f of x and g of x in the given problem, but it's just the standard form of the formula for finding area between curves. That's why I also listed it as integral goes from a to b, upper minus lower dx. If we look here at the graph again, we can see that the region R goes from x equals 0 to x equals 1/2. They will be our a and b values respectively. We can also see that this line is above R, and this one is below. The one above g of x and the one below f of x, as we already determined at the start of this video. And now that we have found those, we can put them into our known integral expression to find the area. So our upper is going to be g of x, and our lower function is going to be f of x. If we plug these into our integral expression, the area will be the integral from 0 to 1/2 sine of pi x minus 8 times x cubed dx. If we split these integrals up, it will be easier to find. I recommend splitting up integrals if they have expressions either subtracted or added to each other, because it can minimize errors and overall make it easier to see. For the sine of pi x, we can use u substitution to find the integral. Note that for now, we are going to ignore the bounds of 0 to 1/2 and find the integrals first. This method allows you to focus on finding the antiderivative correctly before having to worry about plugging in the values. The u is pi x, so du will be pi dx. The dx will then become du over pi. Using these u terms and plugging them into the original integral expression, we can get the integral much more easily than having to work with a sine to the pi times something. The integral of sine is negative cosine, and if we take out the pi from du over pi, we get negative 1 over pi times cosine of pi x as our integral after we plug in the u value. The integral of 8x cubed can be found using the power rule backwards. When we take a derivative using the power rule, we normally bring down the exponent, then subtract 1 from the exponent. But for integrals, we can just add 1 to the exponent and divide by the new exponent value. Note that this is only convenient for simple integral expressions like this, with the x to some power. If there are more complex things like trigonometry or logarithmic functions involved, it is best to use substitution or integration by parts to find the antiderivative. Now that we've found our integrals, we can combine them to get negative 1 over pi times cosine of pi times x minus 2x to the 4th power. Now we can evaluate this from 0 to 1/2. When we plug everything in, we get this expression. Don't forget that the larger number on the bounds, the b value, will always come first. Then the expression with the a value plugged in will be subtracted from that. To simplify the expression, we can use the unit circle. We know that at 0, the cosine value is 1 and the sine value is 0. At pi over 2, the cosine value is 0 and the sine value is 1. For the expression we found, we have only cosine values, so we will only have to use the cosines. Cosine of pi over 2 is 0, which leaves only negative 2 times 1/2 to the 4th power in this first section, where the 1/2 is plugged in. When 0 is plugged in as the x value, which is the second section, in the square brackets, the cosine is 1, which gives us negative 1 over pi minus 2 times 0 to the 4th power. Calculating those values, we get this expression, 0 minus 2 over 16 minus negative 1 over pi minus 0. As our final area of the region R, we get negative 1 over 8 plus 1 over pi. Part C asks us to write an integral expression for the volume of the solid generated when R is rotated about the horizontal line y equals 1. Make sure to read the problems carefully because if you don't, you might end up wasting time trying to calculate the actual volume with an overly complicated integral. This graph to the left shows what kind of solid will be generated if R is rotated around y equals 1. It may be a little difficult to visualize and you might be like, how do I find the volume of this? But that's why we use something called the disk and washer method. A disk is pretty common knowledge, like you know what a disk looks like, but a washer you might be a bit unfamiliar with. A washer used for this method is actually a thin disc-shaped plate with a hole through the center and is used to distribute the load of the screw. It's definitely not those washers you throw your dirty laundry in. Anyways, the way we find the volume of solids of revolution is by thinking there are infinitely many thin discs or washers making up the area, which is what I drew here in purple. This helps me visualize the solid a lot better, which is pretty cool. And in this case, I did have to use a washer with a hole through it because this solid does have space empty in the middle. Now to move on to the problem, there's also a formula used for the volume of solids of revolution using the disk and washer method. Again, we are going to use an integral in terms of x because the functions we were given are in terms of x. The integral is from a to b, which will be the same values we used in part b, and then it is the integral of a of x dx, in which the a of x is the area of a washer, or also known as a ring. The formula for the area of a washer is pi times the outer radius squared minus the inner radius squared. Here's what the inner and outer radius of the area would be. Make sure the radius is determined with y equals 1 as the center, because that is what our region R is rotating around to make the solid. That is why f of x and g of x are subtracted from 1 to get the inner and outer radius. The volume can be found using the integral from 0 to 1/2 pi times 1 minus f of x squared minus 1 minus g of x squared dx. After plugging in f of x and g of x accordingly, this can be simplified to pi times the integral from 0 to 1/2 1 minus 8x cubed squared minus 1 minus sine of pi x squared dx. This is our expression for the volume of the solid of revolution created by R about y equals 1. If you want more practice with problems like this, I suggest you check out the first problem of the 2006 Calculus AB FRQ and the second problem of the 2012 Calculus AB FRQ. I also recommend checking out the website GeoGebra, which helps visualize solids of revolution.